We are ready to begin a brand new chapter, Chapter 8 on Systems of Equations and Inequalities. Now this is definitely going to start out as a review because you already solved equations back in your algebra days in high school and such. So what we're going to do is we're going to kind of recap a few things, and then we'll go into some maybe a little bit deeper meaning on some of these topics. So let me remind you that we have learned different techniques to solving a system of linear equations. In your Algebra 1 days, you learned how to solve systems by graphing, by using substitution, by using the linear combination method, sometimes called the elimination method, sometimes called the addition method. And then in Algebra 2, you most likely did a little bit of work with Kramer's rule and augmented matrices. Well, we're going to save these for another time. We're going to look at the first three here. But before we do that, let me remind you that when we are solving linear equations in two variables, essentially what you're going to do is when you graph, you get a line. And a line has an infinite number of points, which means that there are an infinite number of ordered pairs that correspond to those points, and each one of those ordered pairs is a solution to the equation of the line. Now, because of that, when we graph, and that's the first method we're going to look at, we're going to be able to get a visual of what's going on. But first things first, what is a solution to a system? Well, a solution to a system means that it solves or satisfies both equations in the system, a system being two or more linear equations. We're going to just look at what we call 2 by 2 systems, two equations with two variables. Here's an example of a 2 by 2 system. 3x minus y equals 10, x plus 1/4 y equals 1. And I have two possible solutions here, and the directions say determine if the ordered pair is a solution to the system. Well, to do that, I am going to see if this ordered pair satisfies both equations. Now, when I substitute in, this of course goes in for the x and then for the y over there, but if it does not make the first equation true, then there's no need to check the second equation, and vice versa, because it has to solve both of them. It has to satisfy both of them. So this is my x value, this is my y value. I'll plug in here. That would give me 3 times 2 minus y, which is negative 4. Does that equal 10? Well, that's 6 minus a negative is plus 4. Yeah, this one checks out okay, at least with the first equation. Now I'll try the second equation here. I'll plug the 2 in for the x, plus I'll plug the negative 4 in for the y. So this is 1/4 times negative 4. Does that equal 1? Well, 1/4 times negative 4, I'm going to multiply first. That's going to give me negative 1. And as you can see, this satisfies both equations. Is it a solution to the system? Yes, it is. Don't just tell me yes or no. Always show the work to back it up. Now we'll try answer B here, but if you remember this from your algebra days, you know that about 95% of the time when they give us a system, there's only one solution. So probably this one isn't going to work, but we're going to try it all the same. So I'll plug it into the first equation, 1/3 in for x and negative 9 in for y. I get 3 times 1/3 minus negative 9. Does that equal 10? 3 times 1/3 is 1, minus a negative is plus a positive. Well, 10 equals 10. Maybe this is one of those rare occasions. Let me plug it into the next equation. I get 1/3. Here, I'll put it right here. 1/3 plus 1/4 times negative 9. Does that equal 1? Well, let's see. 1/4 times negative 9 is negative 9/4. I have 1/3 minus 9/4 equaling 1. Well, I can stop right now because I can tell you that's a bigger number than that. So if I subtract, it's going to be negative, and that is not going to work. So this one is no. Here, I'll put it right here. Okay? No, it is not a solution to the system. So again, if it just works for the first one, and you say, well, it's going to work for both, I'll just check the first one. Here's a good example when it doesn't work for the second one, and therefore it doesn't work for the system. Alright, now if you take these two equations, and we've graphed lines before, we normally put them in the slope-intercept form, y equals mx plus b. But if you take these two equations, come on over here, those are the same two equations, the same system. Look what happens when I graph. The equation is in green here. I've color-coded it, and this equation corresponds to the line here in brown. Notice that these two lines, remember each one of these lines is an infinite number of points that corresponds to an ordered pair that's a solution to the equation. Well, in this case, you can see right here that point is common to both lines. That's the guy we're looking for. We're looking for those answers that satisfy both. And if you look over here, this ordered pair, that would be 2 to the right, down 4, 2, negative 4, which we just verified a little bit ago back here that that was a solution. So what we can do is we can graph them. Now, I love graphs. They give you a visual look at what's going on, and sometimes that helps a lot to understand what the problem is doing. The only problem is with graphing, if you're not an accurate grapher, or if you get an answer that would be, let's say for example, the answer turns out to be 1 and 11/12, negative 3 and 9/10. Well, if I was to find that point based on my graph that I have here, even if I use graph paper and such, I wouldn't be able to tell the difference between those two ordered pairs. Because this is so close to 2 and this is so close to negative 4 that graphing wise it's going to look like it's dead on 2, negative 4. And then if I go back to check my answer to see if 2, negative 4 is indeed the solution like I did back here, you know, with this answer, you know, what I might end up having, if this was actually the answer, I'd get close, but I wouldn't get equality. So there's better methods, and that goes back to method 2 on substitution, method 3 on linear combination. There's better methods to do this. This is nice though, you get a picture of what's going on. So if we have a 2x2 system, I wanted to bring into these diagrams right here. When you graph two lines, because a 2x2 system means two equations, two variables, two linear equations, two variables right now, that's what we're dealing with, then you're going to graph two lines. One of three things can occur. As in this example, the two lines may intersect at a single point. When that's the case, there's one solution, like I had here, and we classify this as a consistent system, and we normally refer to it as being independent. If I could spell, there we go, independent. Now it's possible that you graph the two lines and they're parallel and they don't intersect. That means there's zero solutions, and we classify that type of a system as inconsistent. That kind of makes sense. No answers, inconsistent, those are both kind of bad, kind of bad ideas, whereas consistent and a solution kind of matches up. Now it looks like I only graphed one line because you can't probably see that I tried to draw both lines on exactly the same line. I have green and brown arrows to indicate that I have two different lines that turn out to be the same line, that they coincide. And what that means is every point on the one line is a point on the other. There are infinitely many solutions. Every point on the line corresponds to an ordered pair. That's a solution, infinitely many solutions. And we call that type of a system consistent and dependent. Right? And we need to try some more examples of these types.